What is up, calculus students? I got this new lesson video for this new lesson. Very excited about teaching this lesson. Introducing you to an instantaneous rate of change. We are going to finally talk about derivatives, what they mean, where they come from, how we're going to find them. So here we go. We know that calculus is the math of change. We learned last lesson that the slope connecting 2 points, if I have some function and I got 2 points and I find the slope, that we have the average rate of change. We like to say on average, my function is either increasing if we have a positive slope or decreasing if my slope is negative, or neither increasing nor decreasing. Maybe we say it's constant, it's flattened out if the slope is zero. This many y's per x over an interval, average rate of change. What we need to change our focus to what calculus is really about, which is how a function is changing at a point. And this is for the rest of the year. We said the average rate at which a function is changing is like increasing 5 y's per x over the interval 1 to 7. I'm now going to ask you, how is the function changing at x equals 4? Okay, like, is it increasing? Is it decreasing? And how many y's per x is it changing at that location? So no longer are we talking about intervals, like the average rate of change over the interval 1 to 4. I'm going to be like, yo, at 3, what is the rate of change, the instantaneous rate of change? Now, just as a reminder, we always look from left to right when we're analyzing functions when it's coming to turning to increasing or decreasing. I have a very kind of basic, nice looking curving function that we're going to focus a little bit on, which is 12x minus x cubed. And the first question is, at x equals 1. Now, this is not an interval. This is a point. At x equals 1, is the function increasing or decreasing? Well, hopefully you're saying the function is increasing. It's going up from left to right. And if we look at x equals negative 3, at x equals negative 3, you can see the function's going down. Okay, cool. It's decreasing. At x equals 2, x equals 2. It looks like my function is not increasing nor decreasing. It's neither. It's constant. Well, our goal is to write a statement. At x equals 1, the function is increasing and then some amount of y's per x. So it's very much just like what we did last class, but instead of saying on average my function is increasing this many y's per x over this interval, we're saying at x equals 1, the function is increasing, and then you're going to tell me how many y's per x. All right, cool. Well, just like we talked about last class, slopes equal change. We're talking about y's per x, so we want some sort of slope value that gives me a y's per x. Well, then the question is, what the heck is a slope at a point? Can you draw the slope at one point? Well, this is more easily done theoretically than it is like practicality. Like drawing a slope, I bet you guys can do. Now, finding the slope, that's the tough thing. So hopefully you're thinking, okay, if I want to kind of draw a slope just at 1, I'm not connecting 2 points. I'm just looking at x equals negative 3 and x equals 1. Hopefully you're thinking about drawing a line that just touches the function at the point. Drawing a line that just is touching the function at the point. Would that make sense, that that is the kind of the slope of the function at a point? What you've just drawn is called a tangent line. These are tangent lines. Cool. Well, what did I put next? The question is, what are these slopes? Because guess what? The slope of a tangent line, the slope of a line just touching the function at one point, is equivalent to how quickly the function is changing at a point. Not an average rate of change, but an instantaneous rate of change. Instantaneous rate of change. And since it's so important, this concept, it baffled mathematicians for thousands of years until the 1600s, where Newton and Leibniz both discovered it around the same time. Since it was such a big problem, it gets its own special word. Slope of a tangent, which tells you the instantaneous rate of change of the function, we're going to call a derivative. So that's what a derivative is, guys. A derivative is just a slope. It's just a slope. It's the slope at a point, which will tell you how quickly the function is changing at that point. But here's the problem. How can we find a slope if we only have one point? So for example, we have this point 1, and if I plug in 1, I get 11. So we know f of 1 equals 11. I'm going to focus my attention at x equals 1 so we can kind of throw these other lines away. How can we find the slope at one point? Well, here's a problem. If I use like the slope formula, it's like I need 2 points. I have like a y2 and an x2, but like what am I going to use? The same value? Well, I get like this 0 over 0. That's bad. Does that mean the slope doesn't exist? No, it definitely exists. You can see the slope. I can see it's a positive slope. It looks like it's like 1 or something. Actually, the y's are all jacked up, so I don't know exactly what the value is. I know it's positive. So we got to think of a different way. We can't just use the slope formula like we loved doing with average rate of change. So, well, maybe if we had a calculator, we could. If you had a calculator, if you have the ability to work with decimals, what could you do to get a really, really good approximation of the slope at x equals 1? And you need to think about that. It's like, how can I kind of create a line or find a slope of that line that's like really just looking at one point at x equals 1? And the idea is coming from last unit. What did we focus on a lot last unit that helped us talk about maybe not looking at one location, but looking really, really close to that location? Like very, very, very close to that location. Hopefully you're thinking about limits and how with a limit, you don't have to use 1 comma 11. Rather, you could use 1.0001 comma 11.0008999997. Now, this is a very specific number. I'm not just making this number up. It's through a calculator. Let me just shift this so that it looks just like your graph. Cool. So we're focusing at this point 111. Well, we could also go really, really close in the other direction. And then all of a sudden we do have 2 points. Now these 2 points are very, very close to the location at 1, but it's not exactly on the location. Thank you, limit. I could do the y2 minus the y1 over the x2, be very specific, don't just put random numbers down, minus the x1. And I get a number. That's cool. That's cool. Hey. Sure.
Yes. Oh my god, I love these babies.
It's for calculus.
Calculus.
Hey, smash that like button, okay? Be sure to subscribe, okay? So we get 9. Something close to 9. So this is incredible. Because I have a calculator, I actually am able to find that this slope is probably close to 9. And now I can say, oh, at x equals 1, my function is increasing 9 y's per x. Hooray! We just found our first derivative. But there's a problem. We used our calculator. What if we didn't have a calculator? If we didn't have a calculator, this is not a realistic process. Now, I'll tell you this. In the real world, derivatives are found using calculators specifically. If we have real world data sets and there's a function or some sort of equation that represents that real world data set, they use a calculator and they find how that data set is changing at specific points. So in the real world, the calculator is the king because it's so easy to do it. However, we're not there yet. We got to learn the other way of finding these slope values. We got to find this value of 9 without using a calculator. Okay? So we need another approach. And here's what we're going to do. We're going to just start off seemingly doing something completely different. I have the graph of 12x minus x cubed over here on the left. We can see we have x's plugged in that produce these y's, for example, 111. But now I would like to graph the slopes of f at specific x values. So I'm actually going to create a m graph where at x we are looking at the m of f of x. And here's what I mean. At x equals -3, we drew that tangent line. We saw that that slope was negative, right? We don't know exactly what it is, but we know it's negative. Well, at x equals -3, I'm going to plot a negative value. What is the value exactly? I don't know, but we're just going to plot a negative value somewhere. Now we can see that if we are at -2.5, that my slope is a little bit less negative. So maybe at -2.5, I'll plot a little less negative slope. And then we get to -2, and this is a very nice point because at -2, we can see the slope is 0. So I'm going to plot a 0 slope at -2. And we could keep going through this process. Okay, I got kind of like less positive at -1. I got probably the most positive at 0. I got less positive at 1. I get a 0 at 2. And then at 3, I get this negative slope. And all of a sudden, I'm like, oh, cool. I just created something. And let's check. Let's fill in some more points. Look at some more slope values. Positives, less positives, 0 negatives. We can see that we create this graph. Oh, so I have a graph. I have some sort of equation for the slopes of f. Ooh, I would love to know what that equation is. We'll get there in a second. Like x squared. All right, well, we do the same thing. We got this negative slope at -3. We got this less negative slope at -2. We got this less negative slope at -1. Got this 0 slope at 0. We got this positive slope. We got this more positive slope, more positive slope. So maybe it looks like a curve. Maybe it looks like a straight line. I'm not exactly sure. But all of a sudden I realized that there is some slope equation of f. There is some equation for f. Now, what is the power of having an equation for slopes? Well, if I plug in an x value into this equation, I should be able to get a y value that is actually an m. And for this graph, I kind of assume / I know using my calculator that at x equals 1, the slope is 9. Well, guess what? This graph has to have the point 19. So having equations for slopes, that seems interesting. It's almost like we've talked about having equations for slopes in the past. We got a couple more. We got x cubed. We looked at x cubed last unit. Let's see. This is positive, less positive, less positive, 0. So positive, less positive, less positive, 0. A little bit positive, more positive, more positive. A little bit positive, more positive. Okay, cool. So we have this kind of slope graph where if I plug in x's, I'm going to get m's. And if I have this equation for these slopes, it'd be great. It'd be nice to have equations for slope. Let's look at x to the fourth. It's very interesting. It's very much like x squared, only you see how it like slows down a lot quicker. So again, just go with the slopes and just plot the slopes at the points. Take your time here. So it's at -3, I'm very negative. At -2, I'm less negative. At -1, it's like I'm practically at zero, practically at zero, practically at zero until I get to zero. And then I'm like barely positive, barely positive, barely positive, and then more positive at 2, more positive at 3. So again, these are x values, these are m's, these are positive m's, these are negative m's. And here is kind of this slope graph. There is some equation of f of x that if I plugged in the x value, I would get an m. Last one, just for fun, positive, less positive, less positive, less positive, 0 at 2. At 2, there's a 0. Positive, less positive, less positive, less positive, 0 at 2, and then negative, more negative. Now, how do we know this doesn't curve? We don't know right now. Maybe it curves. All we know is that there is some equation for the slopes. And if we had that equation, we can use it to find the slopes. We know that there's equations out there for slopes. We found average rate of change slope equations. Okay? But what we said was like our average rate of change equation, like for your test of x squared from a point x to a point h distance away from x, we said a rock is 2x plus h. Cool? Well, we could say our instantaneous rates of change equals some equation. But it takes too long. And we're going to be using these equations for slopes so much that we're going to use a very special notation for it. And we are going to call it, instead of the instantaneous rate of change of f at x, we are going to call it f prime at x. We are going to say f prime. This is not a 1. This is a tick mark. Prime. We say f prime at an x. This is the instantaneous rate of change of f at x. It means slopes. F's slopes at x. F's slopes at x. So we're going to actually come back up here and say not the slopes of f, not the instantaneous rates of change of f. Rather, we're going to say, hey, what is f prime at an x value? What is f's slopes at an x value? What is f's slopes at an x value? So maybe we say the instantaneous rate of change of f. Maybe we say the slope of f at x. But rather, we are going to use f prime at x. The derivative of f, which means the slope of the tangent, which means the instantaneous rate of change. Cool? Cool. All right. Well, last lesson, we produced equations of average rates of change of a function from x to a point h distance away of x. We used our friend, the slope formula. And if it's just f, it'd be this f of x plus h as the y coordinate. And if it's just x, it would be f of x as this y coordinate. And we use our friend, Mr. y2 minus y1 over x2 minus x1. And we know that like x2 minus x1 is just this x distance of h, or if you did x plus h minus x, you find that it's just h. And boom, this is an average rate of change. Cool? Like, we did this. Just got h. This is familiar to us. You did it on your test. But now, the question is, what if we still want to use that equation? What if I like the equation of the slopes between 2 points h distance away? But we want these 2 points to be practically on top of each other, super close to each other infinitely close to each other. I want this point here to go really, 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 really close to this point there, so that I get a slope. I create a line that can be connected and extended that would look like a tangent line, which theoretically we thought about. What happens to H? Well, H will get smaller and smaller and smaller and smaller so that it becomes a point, or so that it gets close to zero. All of a sudden, we can say, take my average rate of change formula, but let's put the 2 points practically on top of each other by making H approach zero. And all of a sudden, we will be able to produce not an average rate of change equation, but an instantaneous rate of change equation of f at x, which is the slope of the tangent of f at x, which is f's slopes at x, or the derivative of f. The definition of a derivative is just this: the slope and the limit being married together. Cool. Well, let's not go away from what we did. Let's use what we did. Let's look at our average rate of change equation of x squared from x to a point h distance away of x, but then let's see what happens when h approaches zero. All right, cool. You did this on your test. So you had x squared plus 2xh plus h squared. We did not have to use Pascal's triangle for this. Over h. We simplified the x squareds. We divided everything by an h, and we got 2x plus h. And this was the average rate of change of x squared from x to a point h distance away from x. Cool. And we had to, if I looked at the average rate of change from 2 to 5, I would say like x is 2 and h is 5. Well, what if I said, what is the rate of change of x squared at just x equals 2, and I didn't have 5? Well, you'd say h is 0, right? It's just talking about x equals 2. Well, if h is 0, if I take the limit as h approaches 0 of this expression, I now have an equation for the instantaneous rate of change. At x, I have f prime at x. H is gone. We have no distance. The distance approaching 0. Okay, h is 0. So go back and write the equation for the graph of the slopes of x squared at x. And then you're going to tell me, what is the slope of x squared at x equals 3, at x equals -1, and x equals a half? Well, we come back up here and we say, oh, this graph that we were looking at is actually the graph of 2x. And 2x is the equation for the slopes of x squared at x. So, what is the slope at 2? What is this slope value? Well, let's use our slope equation. Let's find the slope of f at 2. 4. This is the point 2, 4. This is a slope of 4. What is the slope of f at -1? -2. Well, this slope here at -1 is -2. Guys, it's that easy. If you have the equation for the slopes, it's actually easier to use them than maybe like you guys didn't like to use it with average rate of change because sometimes the equations got tricky. Well, let's see if our equations get trickier. What is the slope at a half? What is the slope at 3? Well, the instantaneous rate of change of x squared at x is just 2x, or f prime of x equals 2x. And this is the slopes of x squared. It's 2x. What is the slope of f at 3? 6. That's it. What does this value mean? Now we have interpretations, we have statements. We used to say on average, the function was increasing this many y's per x over the interval from this to this. Now we get to say at x equals 3, my function is increasing 6 y's per x. Do you remember the average rate of change equation for x cubed? You had it on your quiz. Maybe you forgot it. Well, let's see. Using Pascal's triangle, we can simplify the x plus h cubed. And we realized, yeah, Mr. Messner, like these average rate of change equations were not very nice to use past x squared because it just got longer and longer and longer and longer. Now we pulled out the h, and it's like, oh man, now I got like this 3xh squared. Now I got this h squared, and now I'm going to divide by h, and yeah, at least the h's go away. But this is, well, this was a lot more cumbersome to use, this equation. The average rate of change of x cubed from x to x plus h was a lot more cumbersome to use. But what if h was 0? What if we were just looking at an x value and we didn't have to worry about h? What if we said, what is the instantaneous rate of change of x cubed at just x, where h is 0? Oh, well, that's just going to be 0, and that's just going to be, oh my goodness. It's just 3x squared? You're telling me the slopes of x cubed are just 3x squared? Yes, I am. And I'm telling you that the equation of this slope graph that we kind of visualized is just 3x squared. And so powerful having this nice, easy equation that can give us the slopes. So, like, what is the slope of x cubed at x equals 2? What is the slope? Well, let's use our slope equation. The slope of x cubed at 2 is going to be 12. How did I get 12? I plugged in 2 in for x. What does that mean? X cubed at x equals 2 is increasing 12 y's per x. This slope equation for x cubed is just 3x squared. The slope at 2 is 12. At x equals 2, f is increasing 12 y's per x. Might as well do x to the fourth. I will remind you what it was. We had the Pascal's triangle, x to the fourth. We had the 4x cubed h. We had 6x squared h squared. So hopefully you're thinking, oh, Mr. Messer, I kind of already know what it's going to be. But maybe you don't. This is the average rate of change equation. And then x to the fourth went away. 1h got divided out of everything. Two, three, 4. This should have been a 4. Just turned this into a 3. And we would get, and you guys didn't like this. It's like, oh, Mr. Messer, this is annoying. Why would I use this huge equation for an average rate of change? Because I got all of these h's. And it's like, oh, annoying to use. But what if h was 0? What if there's no distance from x to h? What if we're just finding the instantaneous rate of change at an x value and the h was 0? We attach the limit to it, and all of a sudden, you got it. We realize that the derivative, the slope equation for x to the fourth, is 4x cubed. And we could go back on our notes and say that's it. But like, what is the slope of x to the fourth at x equals 2? Well, we're not going to use the slope formula. We're going to use the slope equation that we just found when h was 0, started with the average rate of change, and then turned into this. And we're going to plug in 2. And we got 248 times 4, 32. And say at x equals 2, f, which is x to the fourth, is increasing 32 y per x. What about x equals negative 3? 27 times negative 9. Ooh, no. Change that negative 3 to a negative 1. Negative 4 at x equals negative 1. X to the fourth is decreasing 4 y per x. Cool? Now, I'm just letting you know that for tonight's homework, any other f of x out there besides x squared, x cubed, and x to the fourth, I'm going to do the work for you. And I'm just going to tell you, hey, guess what, guys? If we did all of the average rate of change formula and then we said h was 0, we would just get the slope equation, the slopes of f at just x, not x to x plus h, but just x, and the slopes are 12 minus 3x squared for this guy. Cool? You can go back and see the graph that we sketched. Turns out this graph from the previous page, the graph of the slopes, this is 12 minus 3x squared. What number were we looking for earlier? This number 9. Do we see 9 from the equation? I hope we do, because if we know the slope equation for 12x minus x cubed, the slope of f at x is just 12 minus 3x squared. What's f prime of 1? Oh my gosh, there's 9. There's 9. I use the slope formula that we've developed to develop an equation. And now we know at x equals 1, f of x, which is 12x minus x cubed, is increasing 9 y per x. Cool. I'll tell you that for 4x minus x squared, the slopes are just 4 minus 2x. Great. And you can answer these questions by plugging in. If you plug in 2, guess what you get? 0. What does that mean? At x equals 2, we flattened out. Now, you know what would be nice? It's like, Mr. Messer, you tell me that these are the slopes, but like I don't trust it. I can't check. What was great about the average rate of change questions that we had last unit is that we could use the slope formula and plug in points and get the slope, and we could use our slope equation, and we got the same answer twice. Having that ability to check, sweet. I hope you guys did it on your test, where you like found the slope of x squared from one point to another point and used your slope formula. But what's a way to check if we can't use that? Well, we could use our calculator and do 2 points really close to it. But we could also actually do another visualization, which is the equation of a tangent line. Okay, so we know the equation of a line is this. Okay, I'm just going to do it once or twice because I'm running out of time. Well, here's the idea. Could I somehow see, how did this look? It's the other way around, right? Could I somehow see this tangent line at x equals 1, where I know the slope was 9? How could I see that? Well, let's find the equation of this line and let's use Desmos to graph it. And I told you guys to like break out Desmos. And when you're doing your homework, break out Desmos. All right, well, we need a point. And we need a slope. Now, let's confirm What is the slope? The slope was 9. How did we get that? Well, we developed a slope equation. I gave you the slope equation. And we know that the slope of f at 1 was 9. Cool. So that's going to go right here. Don't touch the x, don't touch the y, because we want all the possible x's and y's. But now the question is, like, what is the point? Well, we're talking about x equals 1, so that's easy here. But, like, what's the y coordinate? Oh, yeah. If I plug in x's into my original function, I get y's. So here's an x, here's a y, here's an m. Plug in x's into slope equations, get m's. Plug in x's into original equations, get y's. And we get this. And now what we can see, which is a beautiful thing, is the following. I want that. The equation y minus 11 equals 9 times x minus 1. Change your color. Is our first tangent line equation. We just created this equation of this line, which is just touching my function at this point. This is going to be kind of my way to check things. Make sure it looks right. Okay? So let's do it at x equals 3. Well, we need a point and a slope. I would ask you guys to do this in class. Let's see if we can do it here. Well, what's the y coordinate at 3? Oh, we got to plug in 3. 36 minus 27 is 9. That's interesting. And then what is the slope? Well, I'm going to plug in 3 into this. I got 12 minus 27. Happens to be 27 just because like 3 times 3 times 3 and 3 times 3. But this is minus 15. Ooh, okay, so I think that I have this x, this y, and this m. I got y minus 9 equals negative 15, x minus 3. Y minus 9 equals negative 15, x minus 3. But bam, here is the point. 3, 9. Here is my tangent line that just smoothly tops it. All right, let's do x cubed at x equals 2. Here's x cubed. Here is the point x equals 2. Cool, what is that point? 2, 8? How do I know that? Easily. F of 2 equals 8. What was the slope? Oh yeah, what was my slope equation for x cubed? Now this one I'm going to have you like, not really memorize, but just like, we hopefully have seen it enough that we're kind of comfortable with that just 3x squared being there. But just here's a reminder, and I'll pretty much tell you for your quiz for now. And that means this is the slope of f at x equals negative 2. This is the instantaneous rate of change. If I plug in negative 2, I get positive 12. So I got y minus 8 equals, this is an x, this is a y, this is an m, equals 12 times x minus 2. Y minus 8 equals 12, x minus 2. Well, bam. Let's do it at x equals negative 1. Let's do the same for x squared at x equals negative 1. Well, I know I have the point negative 1, 1. So that covers my y and my x. Now I need to find the slope. Well, I know the slope equation. I've done it, was like 2x plus h. The h goes away. So the slope equation is 2x. That means the slope at negative 1 is negative 2. I'm going to put that right there, and I'm going to see my handiwork done. Bam. Okay, so that's the way to check. Here's the last one that I wanted you to try in class. Here is an example of what you're going to have for homework. I'll give you the function. I'll give you its slope equation. Okay, you just got to know how to use it. What is the instantaneous rate of change of f of x at x equals at x equals 2? Well, this is the slopes of f at x. This is the instantaneous rate of change of f at x. I can just plug in and find the slope of f at 2. And I get negative 10/4, which is negative 5x. What's my statement? At x equals 2. Not on average. At x equals 2. F of x is decreasing 5/2 of a y per x. Cool. What's the equation of the tangent line? Well, f of 5 is 2. F prime of x was negative 10 over x squared. F's slopes at 5 is negative 10 over 25, which is a negative 2/5. I think my equation is y minus 2 equals negative 2/5 x minus 5. I will go to Desmos and see my handiwork. Here's 10 over x. Here is y minus 2 equals negative 2/5 x minus 5. Bam. Okay, so that's it. What you'll be challenged to do more on your homework is to graph these slope equations by plotting slope values. What would f prime look like without knowing the equation? Well, understand slopes that are negative, that are 0, that are positive. So I'd have negative, 0, positive, 0, negative, 0, positive. It looks like I have actually some sort of x cubed graph. Cool. Other things that you're going to be tested on is like, hey, looking at this f, can you order these? Well, we saw that f's slope at negative 3 was negative. Like, what is f prime of negative 3? It's like f's slope at negative 3, the instantaneous rate of change. We saw this was negative. F prime of negative 1 is positive. F prime of 0 is 0. F prime of 3 is very positive, super positive. So I'd have a negative slope that is less than a 0 slope. That is less than a somewhat positive slope. That is less than a super positive slope. And some other questions you're going to see on your homework is, hey, what is this value? What is this value? What is this value? And it's just taking the slope formula and making sure you interpret it. And I think you could do it, and you're going to see it on your homework. And this worked out. Peace.